Now in the second part of this class we will going to discuss the fluid dynamics part, and this means that we will consider the moving fluids. So in this regard I would like to mention that there exist three basic laws: conservation of mass, conservation of momentum, and conservation of energy, that we utilize to define and as well as analyze the moving fluid. So in this class A244 you will cover 1, conservation of mass, and 2, conservation of momentum, and the third, conservation of energy, you will cover in your AE344 next class. Now in order to derive these the equation for these laws, we need a framework, mathematical framework, and that is commonly known as Reynolds transport theorem. So this is the statement of Reynolds transport theorem. It contains several terms like symbols: B, cis, rho density, small b, bv. So in order to understand these, we will define some basic definitions, and also the control volume approach, and subsequently we will derive this equation for Reynolds transport theorem. So in this slide I would like to define several basic definitions. Number one is a system. A system contains the same matter. So for example, if this is my balloon at time t1, and after at some time the air is coming out of this, then here the air, I consider the air here as in another chamber at t2. So this is my system which is under consideration. Control volume, it is a volume of space through which a fluid may flow. So for that purpose, just consider a circular channel through which the fluid is passing through, and this blue dash line is representing the amount of fluid that I am considering for my analysis at a particular time. And control surface is nothing but the surfaces that surrounds the control volume. The Reynolds transport theorem that I mentioned earlier, the equation for that is for a uniform flow across the control surface. However, in several engineering applications, the flow coming out of surface is not uniform. So we will go and derive our Reynolds transport theorem for a non-uniform flow. Now consider a non-uniform surface through which the fluid is coming out non-uniformly, and for our analysis we will consider a small elemental area on this surface. Let's call it del A, small area, and unit normal onto that surface is indicated with the n vector cap. That's a unit vector, and the fluid is coming out with some velocity v. V is the vector of the fluid coming out of that area. Now we would like to evaluate the extensive property coming out and going in to this element. For that purpose we will perform some mathematical analysis. So here is the amount of the extensive property that is coming out of this element has been calculated, and finally an expression in terms of the integral has been obtained for this. Similarly, I will go next and represent the extensive property that is going in. Now similarly, the rate of extensive property going into the control surface can be written like that, and subsequently the difference is provided here by this equation, and for our control volume it can be written like that. Now finally we have obtained the equation for our Reynolds transport theorem in a more compact form. So it is my Reynolds transport theorem. Now next we will utilize this theorem to derive the equations for the conservation of laws and conservation of momentum. Now I would like to derive the equation in integral form for the conservation of mass, and for that purpose I will use the equation for conservation of mass, that is the rate of change of mass with respect to time will be 0. So I have my extensive property. If this is my extensive property that I will set as my mass of the system, then my intensive property will be nothing but B, capital B divided by M. So this will be M divided by M will give you a 1. So my Reynolds transport theorem in this regard can be written as, now this is the equation for my conservation of mass, the integral form, which I have obtained from the Reynolds transport theorem for an unsteady flow, and we will utilize this equation for solving our problem for practical applications.